This sequence defined inductively by a1 is 1 and an plus 1 is given by 1 over 1 plus an. We want to know if it's convergent, and if it is, we want to find its limit. So we could start by taking a look at the graph of the function 1 over 1 plus x, because this is the function f that defines an plus 1 as f of an. And look at the intersection with y equal x. It looks like there is only one intersection and therefore only one possible limit. We start with a1 is 1 and then we plug that inside the function 1 over 1 plus x. We get 1/2, and then I plug 1/2 inside the function and we get 2/3, and we can keep going this way. If I plug 2/3 inside my function, I'm going to get 3/5, and that's a value of a4. And if I plug this 3/5 inside the function, I get a5, which is 5/8. And one more term, a6 in this case, is the image of 5/8, which is 8/13. In any case, you can see already on the picture and also on the value that we're going to have this spiraling type of situation, spiraling around the fixed point. Specifically, you see that a2, which is 1/2, is less than or equal to a4, 3/5, right? 3/5 is 0.6, which is itself less than or equal to a6, 8/13. And on the other end, a3, which is 2/3, is greater or equal to a5, 5/8, and greater or equal to a7, and so on. So it looks like we have the sequence of indexed by even numbers that is non-decreasing, while the subsequence indexed by odd numbers is non-increasing. Well, this is something that we should prove, and prove typically by induction. So we want to show that a indexed by 2n plus 2 is greater or equal to a indexed by 2n. Of course, I'm replacing n by n plus 1 in a indexed by 2n, and I get 2n plus 2. So to show that by induction, we first need to show P1, in other words, that A4 is greater than A2, and that we have already checked. On the other hand, we need to show that if the property is true for n, it is true for n plus 1. In other words, we want to show that if A2n plus 2 is greater or equal to A2n, then A2n plus 4 is greater or equal to A2n plus 2. So I'm starting with what I know, A2n plus 2 greater or equal to A2n, and I'm going to go through the steps that I need to apply the function 1 over 1 plus x. In other words, I start from an, I add 1, take the reciprocal. That's going to give me the next term, but I want to go 2 terms away, so I'm going to have to do that twice. Okay, so we add 1 on both sides and take the reciprocal, and that reverses the order of the inequality. That gives me 1 over 1 plus a2n greater or equal to 1 over 1 plus a2n plus 2. But what I have on the left hand side is a indexed by 2n plus 1, and on the right hand side is a indexed by 2n plus 3. But now we can do that again, add 1 on both sides and take the reciprocal. When I take the reciprocal, I reverse the direction of the inequality, and so we get 1 over 1 plus a indexed by 2n plus 3 greater or equal to 1 over 1 plus a indexed by 2n plus 1. What I have on the left hand side is really a indexed by 2n plus 4, and on the right hand side a indexed by 2n plus 2. So I got the conclusion I want, because this inequality corresponds to property true for n plus 1. In other words, I have proved that my sequence is non-decreasing. Sequence a indexed by 2n. Now at the bottom I have the sequence indexed by 2n plus 1 is non-increasing, and this would have to be done by induction again. We check that that p of 1 would be true, in other words that that a3 would be less than or equal to a5, and then using the same argument we see that using the function 1 over 1 plus x, applying it to the inequality twice, is going to preserve the direction of the inequality. So if I start with a3 less than a5, then I'm going to get this that I preserve this direction for the inequalities, in other words, that I get a non-increasing sequence. Well, essentially it's the same argument, something that you should write down to train. Now, our sequence indexed by 2n is non-decreasing. To justify that it is convergent, we need to also show that it is bounded above. And I claim that it is bounded above by 1, which is something that you can easily convince yourself of looking at the pictures we had at the beginning. And so, to prove that by induction, we need to show that a indexed by 2n is bounded above by 1 for every n, starting with the case n equal 1. a2 was 1/2, so this is certainly bounded above by 1. And now we need to show that if a2n is bounded above by 1, so is a2n plus 2. So we do what we always do, we follow the function 1 over 1 plus x, right? So I start with a2n less than or equal to 1, then I add 1 on both sides, and then I take the reciprocal. When I take the reciprocals, I reverse the direction of the inequality, and I get that 1 over 1 plus a2n is greater or equal to 1/2. But what I have on the right hand side is really a2n plus 1. And then I'm going to do that again. Add 1 on both sides, check the reciprocals, and I get that 1 over 1 plus a indexed by 2n plus 1 is less than or equal to 1 over 1 plus 1/2, which is 2/3. And 2/3 is less than 1. And what I have on the left-hand side is now a indexed by 2n plus 2, and so I have found that if I start from a2n bounded above by 1, I find that a2n plus 2 is also bounded above by 1. In other words, by induction, my sequence of indexed by even terms is convergent because it is non-decreasing and bounded above. And so I can call L the limit and see what L must be. Well, this is the way you go from an to an plus 1, and because I'm looking at just the even terms, I really need the relationship to go from an to an plus 2. But that's not hard to see because an plus 2 is 1 over 1 plus an plus 1, where an plus 1 is itself 1 over 1 plus an. So if I look at the bottom in this fraction and write it as one fraction, I get 1 plus an plus 1 over 1 plus an. So I have the reciprocal of 2 plus an over 1 plus an, which is 1 plus an over 2 plus an. So that's how I go from one term to two terms further. That's the relationship that I'm going to use either for the sequence of indexed by even terms or the subsequence indexed by odd terms. Regardless, the function 1 plus x over 2 plus x is continuous, and I know that my sequence indexed by 2n has a limit L, so L must be a fixed point for that. So L must be equal to 1 plus L over 2 plus L. And now, if I multiply both sides by 2 plus L, I get 2 plus L squared is 1 plus L. Putting everything on one side, we get the quadratic equation L squared plus L minus 1 equals 0, whose solutions, using the quadratic formula, are negative 1 plus root 5 over 2 and negative 1 minus root 5 over 2. So which one is it? Well, you see that the sequence was non-decreasing and bounded above by 1. It started with a positive term, and if I take negative 1 minus root 5 over 2, I get a negative number. A negative number cannot be the limit for a indexed by 2n because this sequence a indexed by 2n starts with a positive value and then is non-decreasing. So the limit has to be negative 1 plus root 5 over 2. That's the limit of the subsequence with even indices. Now we can look at the subsequence with odd indices, and we've seen that with a similar argument we could easily prove that it is non-increasing. And on the other hand, if you look at the picture we had at the beginning of this exercise, it is easy to convince yourself that this sequence is bounded below, for instance, by 1/2, which can be easily proved by induction, setting for the property we want to prove a indexed by 2n plus 1 greater or equal to 1/2. It is true initially when n is 1, because a3 was 2/3, which is greater or equal to 1/2. And to show the inductive relation that when this is true for n, this is true for n plus 1, I'm going to write it maybe a little bit more abstractly. To go from a indexed by 2n plus 1 to the next term in the sequence, which is a indexed by 2n plus 3, you just apply the function 1 over 1 plus x twice. Right? The first time you get a 2n plus 2, and you plug that again in the function to get a indexed by 2n plus 3. The function 1 over 1 plus x is decreasing on the interval, for instance, -1 infinity, and so when you compose it with itself you get an increasing function, and that means that applying this f composed with f to the inequality a 2n plus 1 greater or equal to 1/2, you're plugging the two sides of an inequality inside an increasing function, so that's going to preserve the inequality. On the left hand side we're going to get a indexed by 2n plus 3, on the right hand side the value of f composed with itself at 1/2, which turns out to be 3/5, which is itself greater or equal to 1/2. Therefore a indexed by 2n plus 3 is greater or equal to 1/2, and we have proved by induction that our sequence indexed by odd numbers is bounded below by 1/2. So we can conclude that this subsequence is also convergent to some number that might be something else, even though because the relationship of induction is to apply this function f equal 1 over 1 plus x twice, this limit of this subsequence must be a fixed point for f composed with itself, and we've seen that these fixed points are -1 plus or minus √5 over 2, but here we have something that is bounded below by 1/2, so it cannot have as a limit a negative number, and therefore the only choice is -1 plus √5 over 2, which means that m and l are the same, so the sequence indexed by the even numbers converges to -1 plus √5 over 2, and so does the subsequence indexed by odd numbers, and we have seen that this is enough to conclude that the sequence itself converges to that number, -1 plus √5 over 2. Now it's time for you to turn to homework on sequences.